You might have heard, most of our bodies are empty space. In this episode, I will tell you that it's not just most, but the universe itself is mostly empty. Many physicists today would also tell you that most matter is empty space, including rocks, tall trees, and human beings like you and me. We know that the majority of an atom's mass is concentrated in its tiny nucleus, while most of the space between the nucleus and the electrons is empty. In an atom, the nucleus contributes to over 99% of the mass, but its size compared to the rest of the atom is like an ant crawling around in a football field. Now, you might wonder why such tiny particles can account for so much mass. When we delve deeper into the concept of mass, we uncover even more astonishing answers. We live on Earth, where we can feel the presence of mass. For most people, mass is directly related to the gravitational force they experience from the Earth, which manifests as weight. If we lack exercise and stay up late, our weight might increase. Strictly speaking, our mass increases. When your body gains mass, you would naturally analyze which parts of your body have increased, and most likely, it's due to fat. Intuitively, you can think about how much fat you've gained, and that's how much mass you've added to your entire body, right? However, the more intuitive something seems, the more likely it is to contradict the most basic laws of physics. Let's re-examine the idea that the mass of an object is the sum of its parts. When you cut a watermelon in half, the total mass of the watermelon should equal the sum of the masses of the two halves. If you cut it into 4 pieces, the mass is the sum of the masses of those 4 pieces. This reasoning seems to hold for most cases. But if you cut a watermelon into very small pieces, let's say more than 10 to the power of 23 pieces, something different happens. The reason is that the total mass of the small watermelon pieces not only includes the mass of their individual parts but also the energy that holds those parts together. Let's talk about the rigorous definition of mass in physics. Mass is the property of an object that resists changes in its velocity. When you push something, it accelerates. If you push something else with the same force, and it accelerates less, we say the second object has greater mass. However, having greater mass doesn't mean it's harder to push fundamentally. Our understanding should be the other way around. If something is harder to push, we define it as having greater mass. This property is called inertia, and it's closely related to mass. Now, when we cut a watermelon into tiny pieces, down to the atomic level, the binding energy that holds the watermelon's atoms together can be broken. As a result, the total mass of the cut-up watermelon decreases. In reality, when you cut a watermelon in half, its mass has already decreased, but the change is so small that you won't notice it. However, if you cut a watermelon down to the atomic level, and you measure the mass of each individual atom and add them up, you'll find that the total mass has decreased. This isn't just a theoretical calculation, it has been observed in laboratories. During this experiment, the loss of mass for these particles is relatively small because a watermelon's overall mass isn't that large. In this experiment, if we cut a watermelon into atoms, and then those atoms into protons, neutrons, and electrons, how much mass would we lose? It's approximately 0.01%. But if we start with smaller particles from the beginning, the situation is entirely different. For example, if you split a proton into quarks, as we discussed in the previous episode, up quarks and down quarks, you would observe a tremendous difference in mass. In this case, the mass of the quarks after splitting compared to the original proton is around 1%. The remaining 99% comes from the energy that binds the quarks together. In other words, the energy stored in these binding interactions between particles contributes much more to the total mass than the sum of the masses of the individual parts. It's significantly more, like 2 orders of magnitude greater. This completely defies our intuitive understanding. Imagine you have 3 ping-pong balls, and you measure their masses. You can easily calculate the total mass of all 3 balls by adding up their individual masses. It's straightforward, right? But if you put these 3 ping-pong balls into a furnace with an enormous amount of energy and compress them together, creating a new smaller ball, you will suddenly realize that the mass of this new ball is much greater than the combined mass of the original 3 balls. The reason for this is that the new ball's mass doesn't only come from the original ping-pong ball's masses, but also from the energy that keeps them bound together. If you think about it, if you weigh 150 pounds, the part of your body that has actual mass is only about 1.5 pounds. The vast majority of your weight comes from the energy that holds these tiny particles together. Isn't that mind-blowing? Now, do scientists really understand why most of our mass comes from this energy? Honestly, they don't know. Scientists truly don't know why inertia, mass, and energy are so intricately connected. This is akin to knowing that the speed of light is the ultimate speed limit in the universe, but not understanding why this limit exists or who set it. Alright, your brain might be a little overwhelmed by now. Let's make the impact even more powerful. Earlier, we mentioned that protons and neutrons can be broken down into up quarks and down quarks. But guess what? A quark is not an actual thing. In fact, there's no such thing as a concrete entity at the level of quarks. At this level, physical objects, as we understand them in our daily lives, don't exist in the realm of physics. In our current theories, particles are essentially indivisible points in three-dimensional space. They have zero volume, meaning they have no size. So, imagine that every one of us is made up of particles, yet each particle has zero volume, which means the entire object is empty space, not just mostly empty. Now, consider this. We say there's nothing in physics. What does that mean? You think of an object. It has mass, volume, and mass divided by volume gives you its density, right? Now, if you were to ask an electron, what's your density? This question wouldn't have an answer. Why? An electron has mass, but its volume is zero. In elementary school, you learn that you can't divide by zero, so an electron's density is undefined. Let's take a look at quarks again. In the last episode, we presented a table of quarks. The first row and the first and third columns represent up quarks and top quarks, respectively. These two quarks have the same electric charge, the same spin, and experience the same fundamental forces. The only difference between them is their mass. The top quark's mass is 75,000 times that of the up quark. If you try to understand this from a conventional perspective, you might think that the top quark has greater density. However, in the definition of physics, they occupy zero space. That's the catch. Why does one of them have such a massive mass while the other doesn't seem to contain more substance? This question seems puzzling because particles are not like anything we encounter in our daily lives. When you apply your everyday perspective to basic particles, you encounter these paradoxes. We tend to envision particles as tiny balls with a certain volume, mass, and maybe even color. In summary, our bodies are mostly empty space, and this concept applies to everything in the universe. The mass of an object doesn't merely come from the sum of its parts, it also includes the energy that binds those parts together. At the level of quarks, there are no concrete objects. Particles are points in space with zero volume. All of these notions challenge our intuitive understanding, but they are the fascinating mysteries that physicists continue to explore. While we can measure mass, we still don't fully comprehend the true nature of inertia, the connection between mass and energy, and why our world behaves in such counterintuitive ways. This situation is analogous to knowing the speed of light is a universal speed limit but not fully understanding the reasons behind it or who established this limit. So, there you have it, a glimpse into the captivating world of physics and its mind-bending mysteries. Remember, the more we uncover, the more we realize how much we still don't know. In reality, particles are not as simple as tiny balls. We don't even know what they truly look like because to understand an object's appearance, we usually need to see it. However, when we break down a particle into incredibly small components, their diameter becomes much smaller than the wavelength of light. This means we cannot observe them by emitting light. So, what exactly is a fundamental particle like? This question is not only beyond the reach of physicists but also inherently meaningless. In quantum mechanics, these tiny particles exist as strange wave-like phenomena, pervading the entire universe within a mysterious field. The Ball model fails to explain the rules they follow. For instance, a particle's position is governed by probabilities. You might have a 99% chance of finding it in your room, and a very low probability, like 0.01%, of finding it at the edge of the universe. Moreover, these discoveries are made at the same time. Take, for instance, the strange behavior of tiny particles, which can pass through any object without needing any external force. Their actions are indeed baffling. Modern physics has shown that the particle model is inadequate. Consider the photon, which has no mass, allowing it to travel at the speed of light. But how can something without mass or volume be considered a thing? If you insist that something must have matter, i.e., mass, then you'd conclude that particles without mass cannot exist. But let's open our minds a bit and consider that mass might not be an intrinsic property of matter but a label we assign to it. This shift in perspective is crucial. We have already adopted this approach in other areas, like when we discuss particle charges. We know electrons carry negative charge and protons carry positive charge. But what exactly is this charge? Is it located on the surface or inside the particles? What bestows the charge on electrons? Since electrons have zero volume, how can they accommodate this charge? In reality, nobody asks these questions because charge is not a tangible thing carried by electrons. It's just an observed phenomenon given a mathematical label. It's like observing a banana's color. We don't claim the banana carries a yellow substance, we just label the color we observe. Applying a similar perspective to mass makes sense. Just as charge means a particle can be influenced by an electric field, mass means a particle can be affected by gravity. An object's charge determines the strength of the force it experiences in an electromagnetic field. Similarly, a particle's mass gives it inertia, meaning it resists motion in a gravitational field. When we mention the top quark being much heavier than the up quark, it doesn't imply that the top quark contains more mass. It merely means the top quark resists movement more within the gravitational field. It has greater inertia. It's just a label. Now, let's talk about something cool, the Higgs boson. But before that, let's discuss force-carrying particles. In the previous section, we mentioned matter being composed of 12 fundamental particles, all falling into the category of matter. But in our universe, apart from tangible matter, there are 4 fundamental forces: gravity, electromagnetism, strong nuclear force, and weak nuclear force. So, how are these forces transmitted? Scientists discovered that force transmission also requires particles. Imagine an up quark and a down quark throwing basketballs at each other. When the up quark throws a basketball, it pushes the down quark outward. In this process, the up and down quarks never directly touch each other. They exchange basketballs to convey their influence. Of course, this is an analogy for the macroscopic world. The actual mechanisms in the real world are not exactly like this. So, what particles transmit these forces? Photons transmit electromagnetism, gluons mediate the strong nuclear force, and W and Z bosons mediate the weak nuclear force. However, scientists haven't yet found the particle responsible for transmitting gravity. But humans are great at making lists, so they created a table and noticed a missing particle. This led to the frantic search for the Higgs boson, earning it the title of the best example of how scientific progress benefits modern civilization, according to the New York Times. Humans created a table based on scientific theories, predicting the existence of a particle before actually discovering it. This underscores how the search for patterns guides our understanding of the universe. As for the process of finding the Higgs boson, it was quite convoluted. In simple terms, the idea originated from studying force-carrying particles like photons and bosons. Some of these particles had no mass, like photons, while others had significant mass, like bosons. Yet, they all played a role in transmitting forces. So, why do some have no mass while others have substantial mass? Physicists, including Peter Higgs, spent a long time and eventually found a self-consistent solution within the mathematical framework. They introduced a new particle, the Higgs boson, and a new field, the Higgs field. Then they used mass as a label for particles, defining mass as the property that varies among particles. However, it's crucial to reiterate that this is just a mathematical definition, not an indication that some particles have more substance than others. Let me explain the Higgs field in simpler terms. It posits the existence of a pervasive field throughout the universe, which doesn't attract or repel anything. Its sole function is to make particles harder to accelerate or decelerate. This field's effect manifests as the inertia of matter, i.e., its mass. In the previous section, we discussed how particles interact with the Higgs field, and the more they interact, the greater their inertia becomes, resulting in a larger mass. Some particles interact strongly with the Higgs field, making it harder for them to accelerate, and thus they have a larger mass. On the other hand, some particles barely interact with the Higgs field, making it easier for them to accelerate, and they exhibit almost no mass. However, the Higgs theory does not explain why different particles have different masses. It seems like mass is just arbitrarily assigned to them. But let's imagine a future where we discover more fundamental particles and their governing rules. These underlying rules might explain why quarks have different masses. For now, we haven't found these fundamental rules, and the mass assignment seems like a random label. It's like asking why one drink is apple-flavored and another is peach-flavored. An expert in drink formulations might know that different flavors result from adding different spices. Similarly, future scientists might reveal that the different masses of particles result from underlying rules we have yet to discover. Now, let's talk about measuring mass. There are two methods. One is to measure the inertia, which means pushing an object to see how easily it accelerates. The other method is simpler, directly measuring its weight using a scale, essentially measuring how much Earth's gravity attracts it. The greater the mass, the stronger Earth's gravitational pull on the object. You can think of gravity as similar to charge. When two particles have charge, they attract each other with a force proportional to the amount of charge. Similarly, when two particles have mass, their gravitational attraction is proportional to their mass. However, inertia mass and gravitational mass are not the same. In our current theory, inertia mass arises from the interaction between a particle and the Higgs field, representing how much the particle resists being accelerated by the sticky Higgs field. On the other hand, gravitational mass comes from the interaction between a particle and the gravitational field. When we have an object's mass, we find that the inertia mass precisely matches the gravitational mass, despite being defined in two different theories. An experiment on the Moon, where there is no air resistance, illustrates this matching. If you drop a light plastic ball and a heavy iron ball on the Moon, you'll notice they both hit the ground at the same time. This happens because the iron ball's gravitational mass is greater, so the Moon's gravity pulls it more strongly. However, the iron ball also has greater inertia mass, making it resist acceleration more strongly. Conversely, the plastic ball is easily accelerated, but its gravitational mass is small, resulting in a weak gravitational pull. The effects of inertia and gravity precisely cancel out, allowing both balls to hit the Moon's surface simultaneously. So, why do inertia mass and gravitational mass perfectly match? That's one of the intriguing mysteries in science. Currently, our understanding cannot explain this phenomenon. We assume they are identical without violating any physical laws. Just like Einstein assumed the constancy of the speed of light and deduced the special theory of relativity, then assumed the equivalence of inertia and gravity mass, leading to the general theory of relativity. If you asked Einstein why he made those assumptions, he would simply say, "There's no why, I believe in it." We accept this match as a fundamental fact without a deeper explanation. To summarize, mass has some peculiar aspects. First, it includes not only the mass of its constituent parts but also the energy that binds them together, and we don't yet know why. Second, mass behaves like a label. In the Higgs theory, it's similar to the charge of a particle. Some particles have a high mass label, making them more difficult to move within the Higgs field. Others have a low mass label, making them easy to move. But again, we don't know why. Lastly, we find that measuring inertia mass and gravitational mass results in exactly the same values. This is one of the most fascinating aspects of science and why scientists have never stopped exploring throughout history. As we delve deeper into these mysteries, we encounter more questions and occasionally stumble upon unexpected answers. Perhaps one day, when we solve the mystery of mass, we'll stumble upon even more remarkable theories. For now, let's leave it here, and in the next episode, we'll delve into the enigma of gravity.